we are jumping straight into the core of the Step-GUI technical report from the GLab team.
Right.
Our focus today is unpacking what looks like a really complete framework for building highly capable and, I think most importantly, practical agents for GUI automation.
And this report is it's so significant because it goes right after the foundational challenge in training these huge multimodal models for multi-step tasks.
Which is always the data, right?
It's always the data. How do you generate reliable, scalable, high-quality data? And they tackle this with a self-evolving training pipeline.
And the engine behind that pipeline is the Calibrated Step Reward System, or CSRS.
Mm-hmm.
The system is just amazing. It converts raw model-generated attempts into these powerful training signals, and they're getting annotation accuracy north of 90%.
And it slashes the cost.
Yeah.
We're talking by a factor of 10 to 100 times compared to human annotation.
It's that scalable data factory we've been waiting for.
And with that data engine running, the resulting Step-GUI model family, which is built on the Qwen 3 VL architecture, it just delivers state-of-the-art performance.
Okay, so what are the numbers?
The 8 billion parameter version hit 80.2% on Android World and 48.5% on iOS World using PASS at 3.
And critically, that smaller 4B model is actually consumer grade. You can deploy it.
Exactly.
They also seem to have solved the deployment and the privacy puzzle. They introduced this thing called GUI-MCP.
The first model context protocol for GUI automation. It uses this hierarchical dual-layer architecture to standardize interaction.
And that enables a high privacy mode, which means sensitive data like your raw screenshots.
They never leave your device.
Which is huge.
And finally, they raised the bar on evaluation with AndroidDaily. It's a new benchmark grounded in real-world high-frequency usage. Think, transportation, shopping apps.
Okay, so let's unpack this. Let's start with that central bottleneck, data acquisition.
Yeah.
We know training agents for these multi-turn GUI tasks is, well, it's notoriously difficult. Why is getting reliable trajectory data so much harder than, say, training a model to just identify a cat in a photo?
Well, it's a whole different ballgame. It really comes down to context longevity and having a verifiable ground truth.
Okay.
I mean, if you're training a simple classifier, the ground truth is binary and immediate. Is it a cat? Yes or no.
Right.
But in a, say, 15-step GUI task like booking a flight, an error you make in step 2, like clicking the wrong date field, it pollutes that entire sequence.
And the model's own reasoning can't be trusted.
Exactly. If the LLM generates a trajectory and the whole thing fails, how do you trust the thinking steps it gave you? That reasoning is just prone to factual errors or hallucinations because it can't verify its own execution path in real time.
And having a human annotate all 15 steps is just way too expensive and subjective to scale.
Impossible to scale. So the core idea of CSRS, the Calibrated Step Reward System, is to anchor that dense, fine-grained reasoning from the LLM to a much simpler, more robust signal.
Just did the whole thing work or not?
Exactly. Did the trajectory succeed or fail? That's the insight. You leverage these coarse-grained, high-confidence labels to validate all the fine-grained data.
And it does this with a two-part architecture. The first is the calibration layer.
Right. And this layer uses automated scripts, or maybe some light human oversight, to provide a simple binary outcome, success or failure. And that course validation is super accurate, over 90%.
Because that gives you the high confidence signal you need.
That's the anchor.
So once you have that success-fail signal locked in, the data extraction module takes over. How does this turn one successful run into 7 different categories of training data? What are they even extracting?
It's pretty incredible. The module uses these sophisticated thinking models to generate all this structured data based on that verified outcome. They're generating everything from progress tracking and state summaries to self-reflection and, of course, the action prediction itself.
It's like a 7-part debrief for every single step.
A meticulous log entry, yeah. And the brilliance is that all 7 parts are now anchored by that high-confidence trajectory label from the calibration layer. You know it's good data.
Which brings us to their selective learning strategy. So if the flight booking succeeds, you get all 7 data types. But what happens if it fails? How do you learn from the mistake without just encoding the bad action?
And that's absolutely crucial for stability. If a trajectory is successful, they extract all 7 types. They reinforce the model's knowledge and its action policy.
Oh.
But if it fails, let's say it clicked the wrong payment button, they only extract the knowledge-related data, so categories 1 through 6.
So the reflection, the summary.
Yeah.
All the why it failed stuff.
Right. You keep that so the model can understand why it failed. But you throw away the action prediction data. The philosophy is simple. Learn the knowledge from your mistakes, but never ever train on the erroneous behavior itself.
That makes so much sense. You want the model to diagnose its failure, but you don't want to reinforce a bad click.
Exactly.
And this LLM-generated knowledge, it's not just a cost saver, it's actually higher quality.
Oh, vastly richer context.
Yeah.
A human annotator might just say, click the save button. The CSRS, with its thinking model, provides a full chain of thought. Something like, I have filled all required fields the user wants to save. I will click the green button labeled Confirm and Save in the bottom right corner.
That dense reasoning moves it beyond just pattern matching.
It's about understanding the semantics of the interface and the logic of the task.
Okay, so CSRS is a reliable, self-scaling factory for high-quality data. Now let's get to how the Step-GUI model actually consumes it. It's a progressive three-stage training paradigm. Why 3 stages?
It's all about strategic progression. You move from these broad strokes to hyper-targeted refinement. Stage 1, mid-training, is all about foundational capabilities.
So just getting the basics down.
Pretty much. They consolidate a ton of world knowledge. We're talking 11.2 million samples, and acquire fundamental visual competencies like object grounding. This stage just makes sure the model can see, understand, and parse agent-style formats across different operating systems.
So that's the broad foundation. Then the focus tightens in stage 2. Cold start fine-tuning.
Precisely. Now you shift from general exposure to error-driven refinement. The data mixture is smaller here, about 1.67 million samples, but it's heavily weighted toward knowledge data.
So this is where they patch the weaknesses.
It's the error diagnosis phase. When a model fails, those failures are diagnosed, and the missing knowledge is converted into visual question answering pairs. They use this small, high-quality, targeted data to patch the blind spots directly.
This whole structure, it really points to that self-evolving closed-loop data engine they show in Figure 3. How does that feedback loop work?
It's 2 parallel data flows running continuously. You have the generation data flow, which is the engine of growth.
Okay.
The current model generates new trajectories, CSRS verifies them, and that high-quality data feeds the next training round. So a stronger model generates better data, which trains an even stronger model.
The flywheel effect again.
It's that virtuous cycle.
And the second one, the refinement data flow, that seems key for stability.
It's the intelligent filter. Existing data goes through self-distillation and rejection sampling. The easy, high-confidence samples reinforce the model's foundation.
And the hard ones.
The challenging samples, the ones near the decision boundary where the model struggled, the rejected set, they get routed back exclusively to that cold start stage for targeted, error-driven enhancement. You force the model to relearn its hardest lessons.
Okay, that brings us to the final step in training, reinforcement learning with verifiable rewards, or RLVR. A sparse success signal isn't enough here, so how do they make the reward signal dense?
Yeah, sparse rewards are a nightmare for credit assignment. You need dense, continuous feedback. So they build a composite reward function with 3 crucial signals. The first is spatial geometric dense rewards.
That sounds technical. What is a quartic decay function, and why do you need it?
Think about it like this. The model needs to click the precise center of a tiny button. If it misses slightly, that's okay. If it misses by a lot, that's a disaster. The quartic decay is a function where the penalty increases exponentially as you move away from the target. It harshly penalizes even minor deviations. It's all about minimizing that distance to the target coordinate.
So that's dense feedback on the where. The second signal is about the what? Action semantic mixed rewards.
Correct. This gives feedback on what the model actually did. It gets a sparse reward for the action type, click, slide, or type. But then it uses adaptive value modeling for the parameters.
How does that work for, say, a SI2 action?
They use cosine similarity to check if the slide vector aligns with the required movement. For something like typing text, they use an external LLM as a verifier to check the accuracy of the content itself, which gives a score between 0 and 1.
So they're verifying the semantics, not just the pixels. And the third signal?
The soft capability rewards. I mean, we want the agent to feel natural, right? Coherent. So they use another LLM as a judge to evaluate abstract qualities like intent, consistency, fluency, and reasoning quality. Things a hard rule can't score.
Okay, now, we have to talk about the algorithmic enhancements here. This is where they tackle the instability of RL in these long GUI tasks. Let's start with semi-online exploration with hindsight.
Right. So in these long sequences, a lot of your exploration just fails. And a failed rollout gives you almost no learning signal.
It's a waste of compute.
It's a total waste. With hindsight, when a rollout fails, they do a second pass. And during this pass, They inject ground truth hints, basically guiding the model through the steps it should have taken.
Ah, so you turn a failed exploration into a perfect guided sample.
Exactly. It's a way to generate these high-advantage trajectories the model could never find on its own, and it accelerates learning dramatically.
In the gradient preservation strategy, why is it so important to protect the gradient for rare actions?
So in RL, you have something called gradient clipping to keep training stable.
Yeah.
But in these complex environments, some correct actions are just naturally rare, very low probability. If the model performs one of these rare correct actions, the standard clipping process might just zero out the gradient. It basically tells the model to forget a potentially valuable move just because it was rare.
Which you definitely don't want.
Right. So their preservation strategy retains a scaled gradient even past the clipping threshold. It ensures there's always a continuous learning signal so the model can reinforce those rare but crucial decisions.
Fascinating. So Step-GUI is powerful, but power is useless if it's hard to deploy and people don't trust it. Let's talk about the deployment framework. GUI-MCP.
GUI-MCP is so critical because it standardizes everything. It's the first dedicated model context protocol for this space, and it uses a hierarchical dual-layer architecture.
Tell me about that division of labor between the layers.
So at the bottom, you have the low-level MCP. This is your toolbox of atomic operations. Click, swipe, input text,
The building block.
the building blocks. This gives a big, powerful main LLM maximum flexibility for detailed planning.
And the high-level MCP seems to be where the intelligence gets distributed.
Precisely. The high-level layer uses an execute task interface. So instead of a massive cloud LLM handling every single click,
You delegate.
you delegate the task to a locally deployed, specialized GUI model, like their Step-GUI 4B. The main LLM does the high-level planning. The local model does the rapid routine execution.
Which cuts down on API calls, latency, cost.
Flashes all of it.
The high privacy mode has to be the killer feature here for real-world adoption. How does GUI-MCP prevent my banking app screenshots from being sent to a cloud model?
This is the core of the privacy guarantee.
Wrong.
External cloud LLMs are strictly, completely denied access to raw device screenshots or any detailed unmasked information.
So what do they get?
The local GUI model processes all the raw input on your device and only sends back state summaries, key semantic information to the cloud LLM for high-level reasoning.
So if I ask my agent to find the cheapest flight, the cloud agent delegates, the local agent does all the clicking and typing.
Right. He does the 5 steps, opens the app, searches, browses, completes.
And it only sends back the final price and flight title, not a single image of my screen.
Exactly. That localized execution and semantic filtering means you maintain privacy while still getting the benefit of the powerful cloud model. It's a necessary division of labor for trusted AI.
Okay, finally, evaluation. The numbers are impressive, but they also introduced a whole new benchmark, AndroidDaily. Why did we need that when Android World already existed?
Well, Android World and similar benchmarks tend to focus on utility apps and tasks that can feel a bit contrived.
A bit sterile.
Yeah. AndroidDaily addresses that gap between lab tasks and authentic everyday usage patterns. They focus on high-frequency, complex scenarios like navigating a transit app or comparing prices on a shopping platform. Messy, ambiguous stuff.
And they have 2 evaluation modes, static and end-to-end.
The static benchmark has over 3,000 actions, and a key innovation is that it supports multi-solution ground truth.
Meaning if there's more than one right way to click a button, it counts them all as correct.
Exactly. And the end-to-end benchmark uses 235 complex tasks and an LLM-based judger to assess real-world success with much higher fidelity.
Okay, let's talk numbers. The Step-GUI 8B is outperforming much larger models. So what does that 80.2% on Android World pass at 3 actually mean?
So pass at 3 means the model gets 3 chances to succeed at a task, which kind of reflects how a human might try a few times.
Okay.
That 80.2% is a huge milestone. But what's really telling is the 48.5% on OS World Verified. That shows its robustness in really complex OS environments. It's punching way above its weight class.
And on their own benchmark, AndroidDaily.
The 8B model scores almost 90% on static action prediction, which confirms it has superior domain knowledge for mobile operations, and it's much better at handling underspecified instructions, which is where things usually fall apart in the real world.
Looking at the training dynamics chart, figure 7, there's this massive jump of phase transition on Android World between round 2 and round 3. It goes from like 45% to over 73. What happened there?
That phase transition is the proof. It's the tangible evidence of that CSRS data flywheel kicking in. Once the model hits a certain capability threshold, say 40 or 50%, it becomes reliable enough to consistently generate verifiable successful trajectories on its own.
So it starts teaching itself.
These self-discovered high-value samples flood back into the system, and that's what catalyzes that explosive growth. It's the model feeding its own intelligence.
I have to ask, though, specialization like this often comes at the cost of generalization. Did all this GUI training hurt its fundamental multimodal capabilities?
That's the critical question, and according to their evaluation, no. Step-GUI 8b either maintained or even slightly improved its general multimodal capability compared to its base model.
Yeah, it's surprising.
It scores 89 on the V benchmark, holds strong on OCR bench. The progressive training managed to add deep GUI expertise without a trade-off, without compromising that general knowledge base.
So to wrap up, we've laid out a complete framework. You have a self-improving data loop with CSRS, you have state-of-the-art models with Step-GUI, and a standardized, privacy-aware deployment layer with GUI-MCP. This isn't just another paper about accuracy.
No, it's a new system design. It absolutely establishes a crucial new paradigm for building agents. They've created a pipeline where compute resources are efficiently transmuted into high-quality data, which is the real fuel for intelligence.
And that 4B model being deployable locally.
That is arguably the most significant step towards having ubiquitous, trustworthy AI assistants that just live on our devices.
So if the bottleneck of generating high-quality, long-horizon data is now effectively solved by pipelines like CSRS, that leaves us with a provocative thought. What fundamental limits are even left in achieving a truly autonomous, trustworthy agent that can handle any daily digital task without needing constant human oversight?